Thank you for attending my talk. I'm going to talk about the copy number transformation problem. I will first present the definition of this problem and its relevance to this workshop. And afterwards, I will discuss the algorithm we obtained to solve it efficiently. And this is a joint work with Ron Shamir and Ron Zehavi from Tel-Aviv University. So before presenting the definition of the problem, we need the following definitions of copy number, CNs. So a copy number profile is a vector where the entry and at the ith position, Vi, is the number of copies of gene I. And we assume that Vi is a non-negative integer. So for example, here we have 2 copies of the second gene in this copy number profile. An amplification is a triple LH1. The third argument is always 1. And its range includes every integer between L and H, including L and H. Now, given a copy number profile, it increments by 1 the value at each entry that belongs to its range, unless this value is 0, in which case it remains 0. So, for example, here we increment by 1 the values at the 3rd and the 5th entries, and the value in the 4th entry, which is 0, remains 0. And deletion is defined similarly. Now we decrement by 1 the value at each entry that belongs to the range, unless it is 0. Now, a genome can evolve over time using a series of modifications called rearrangement, and combinatorial and algorithmic methods to detect this series have been the subject of extensive study in the last 2 decades. Here I just want to mention that the majority of the models either assume that each gene has a single copy or result in an NP-hard problem. So these models are limited in their ability to handle complex genomes such as cancer, and it is also appropriate to consider distances between copy number profiles. Now, before I define such a distance, I also want to mention that there are well-known methods to detect copy number profiles, and that, however, algorithmic aspects of questions related to these distances gained little scientific attention to date. And here we will use a known definition that is based on segmental amplifications and deletions, which we will see on the next slide. So to present the problem formally, let S and T be 2 copy number profiles. Now, a copy number transformation from S to T is a vector C of M amplifications and deletions for some non-negative integer M, such that when we apply these amplifications and deletions one after another, first C1, then C2, and so on, starting at the copy number profile S, we will obtain T. Here you can see an example of such a transformation from S to T, where red and green blocks indicate deletions and amplifications respectively. Okay, so we get from S to T. Now, as expected, the distance from S to T is the smallest side of a copy number transformation from S to T. And the copy number transformation problem asks us to compute this distance. And one can also want to obtain a transformation that realizes this distance. We showed that the copy number transformation problem can be solved in linear time and constant space. Now, to this end, we use 3 steps. First, we prove several 4 key propositions about the nature of the problem at hand. And using these propositions, we obtained a dynamic programming-based algorithm. These are its time and space complexities, where capital N is the maximum copy number in the input. And afterward, by using piecewise linear functions, we improve this algorithm and obtain our main result, a linear time constant space algorithm. Now, I will say a few words about each step. Before them, there is a certain preprocessing step that I'll skip due to lack of time. So let's look at the proposition. So the first proposition states that it is sufficient to look at copy number transformations where all of the deletions precede all of the amplifications. Now, when you think about the opposite proposition, stating that it is sufficient to examine copy number transformation where all of the amplifications take place before all of the deletions, then this proposition is not true. And you can see this by looking at this example, which we've already seen in a previous slide. And you can see that here we have a copy number transformation of size 3. But if you demand that all of the amplifications will take place before all of the deletions, then it is no longer true. You cannot find a copy number transformation of size 3. And the intuition behind this is that we want to reach 0 values as soon as possible, because it doesn't matter if we have an amplification or a deletion, they stay 0. So this is why we want to have deletions as soon as possible. Now, the second proposition states that it is sufficient to examine copy number transformations that do not contain both a deletion that affects Si but not Si plus 1 and a deletion that affects Si plus 1 but not Si. And the same is true for amplifications. Now, if you look at a copy number transformation where all of the deletions take place before all of the amplifications, then it is actually very easy to see that this proposition is true, because in this case you can just replace such two deletions by 1 and obtain a shorter copy number transformation. If we are looking at the index I such that Ti is greater than 0, then, and we know how many deletions affect Si when we want to reach Ti, then we can compute exactly how many amplifications should affect it. However, if Ti is 0, then this is no longer true. Okay, we can know how many deletions affect Si, but we cannot compute exactly how many amplifications should affect it. But in this case, we have a proposition that actually states that we do not have to store information about how many deletions and amplifications affect Si if Ti is 0. And here I do not give the precise statement of this proposition, just this implication. And finally, our fourth proposition states that the maximum number of deletions and amplifications that can affect each Si can be bounded by n, where recall that capital N is the maximum copy number in the input. Now, by using these propositions, we can obtain a recursive formula that naturally leads to the development of a dynamic programming-based algorithm. And the idea is that we use a table M that has an entry for every index I between 1 and n, and for every d between 0 and capital N. And in this such an entry, we want to store the size of an optimal transformation from a prefix of S to a prefix of T, taking the first I entries, and such that exactly the deletions affect Si. Now, I won't discuss the recursive formula and the notation in details. I just want to mention that when we compute such an entry, we just look at the previous index where Ti was not 0, okay? And we look at the best D prime that we can choose, the best number of deletions that correspond to this entry. And to this already computed value, we add values that correspond to the number of new deletions that we need, the number of new amplifications that we need, and another value that is related to the 0 entries in T that appear immediately before the Ti, the value at the entry I. Now you can see that we have here this number of entries, and each of them can be computed in this time, okay? Because we have this minimization here. So we obtain this running time, okay? But we want to obtain an algorithm, a linear time algorithm that has a constant space. So to this end, we use piecewise linear functions. And the main idea is that we show that the table M can be described by ON piecewise linear functions, where each of them encapsulates O of capital N entries. And we also saw that each such function is well behaved. This means that it just has 3 linear segments. Okay, so now instead of looking of O of capital N entries when we compute one entry in the table, we can only look on one well-behaved function, and therefore the time to compute it is now constant. Okay? Moreover, we showed that now the size of the table shrinks. Okay, we just have this number O of n functions to compute. And therefore, because we have this number of new entries of functions, and each of them can be computed in constant time, we obtain a linear time algorithm. And it can also be shown that it is a constant space algorithm. Okay, so this is our main result. And thank you for your attention.
Hi. Very nice talk. I have a quick question. So suppose I'm given 2 copy number profiles, and I cannot transform one into the other. What is the hardness of finding like a standard problem? So a copy profile that is an ancestor of both, and then basically from that ancestor you want to get the first copy profile and the other one, such that the number of events, the total number of events is.
Oh, this is a great question, and we are currently working on it. Okay.
Can I just plug in there? Because thanks for, so I'm the Schwartz from the Schwartz et al. We did that actually to follow up on that question. We used this dynamic programming implementation, and it's great to see that we're continued. And I think particular because the complexity is very high when you want to do the ancestral reconstruction to get the minimum tree that has the shortest overall tree length.
Yeah, especially if you have multiple ancestors.
Exactly. So for the same reason why traditional phylogenetic with indels is complicated, because we had a finite state machine representation, then your state space explodes and so on. You need to prune when you walk up the tree. Such an algorithm would be very, very useful to do an efficient ancestral reconstruction, which we have to use heuristics for because of this complexity issues. So we have a solution, but maybe we can find a better one with this addition.
So maybe I will add another, more details. So what I said that we are currently working on is an algorithm with an efficient time complexity, and we have several directions. So if you want to talk about it later. Okay. Yes.
Have you considered looking at copy neutral alterations, like inversions of the copy?
This is another direction that we might look at. Currently, we are working on previous suggestion.
Question is when you select a region for changing the copy number, you assume that all intervals are equally strong, like that there's no guarantee, but could you comment on what would happen if you didn't have that assumption? Could you still, I think you can still do it in time that's proportional to big N, but can you still do all of that?
So I'm not sure that in this case we can still describe the table using piecewise linear functions. So it is possible that time complexity wouldn't be linear anymore.
So you showed the third argument in each operation was 1 or -1, right? But if you could have like different amplifications of like 3 times the copies or something like that, increments.
So it's just 3 operations that we already considered. But if you want to give them a different weight, for example, for 3 operations to give the weight 2, then it's a bit different.
Okay.
Okay, so let's thank the speaker again.